Welcome to today's video, where we'll be exploring one of the most intriguing moons of Jupiter, Callisto. For students studying astronomy, planetary science, and moon formation, Callisto offers a fascinating case study. As the third largest moon in the solar system, Callisto has some unique characteristics that make it a prime subject of study. This video will delve into Callisto's surface features, composition, history, and the scientific discoveries that make it stand out as one of the most ancient and well-preserved bodies in our solar system. Callisto orbits Jupiter at a distance of about 1.88 million kilometers, about 1.17 million miles, making it the outermost of Jupiter's four Galilean moons, which also include Io, Europa, and Ganymede. Unlike its neighbors, Callisto has not experienced much geological activity for billions of years, which makes it a pristine record of the early solar system. This provides students with a rare opportunity to study a celestial body that has remained mostly unchanged since its formation. As you learn about planetary history and moon evolution, Callisto's lack of internal heat and geological activity makes it a particularly valuable subject for understanding the conditions of early moons and their environments. When we talk about surface features, Callisto's landscape is dominated by impact craters, with the most prominent being the Valhalla crater, a multi-ring structure nearly 3,000 kilometers 1,864 miles in diameter. The surface of Callisto is one of the oldest and most heavily cratered in the solar system, and its craters offer important clues about the history of impact events and the early bombardment period that affected not just moons but also planets. Students studying planetary geology can learn a lot from Callisto's surface. The craters here are not eroded or altered by volcanic or tectonic activity, which means they have been preserved for billions of years. This is in stark contrast to many other moons and planets, where geological forces have reshaped the surface over time. Callisto's lack of significant geological change offers a snapshot of the solar system's early history, providing students insights into how moons and planets evolve or fail to evolve over time. Another critical aspect of Callisto is its composition. Callisto is made up primarily of rock and water ice, with a relatively small metal content compared to some other moons like Ganymede. Beneath its icy surface, scientists believe that Callisto may have a rocky core surrounded by a thick layer of ice. This combination of ice and rock makes Callisto one of the many bodies in the outer solar system that may have a subsurface ocean, though unlike Europa, which has been found to have an active ocean beneath its icy crust, Callisto's potential ocean is thought to be quite static and frozen. This is a key difference between Callisto and its more geologically active neighbors. For students studying planetary composition, this distinction is crucial. Callisto's composition may hold the key to understanding the varying characteristics of moons that orbit gas giants and how gravitational interactions with their parent planet, like Jupiter, impact their internal heating and geological activity. What makes Callisto even more interesting is the mystery of whether it could harbor the conditions necessary for life. While there's no direct evidence to suggest life exists on Callisto, its subsurface ocean could provide an environment where life, similar to the life we find in extreme conditions on Earth, might thrive. For students of astrobiology, studying Callisto is essential when considering the potential for life elsewhere in the solar system. Its subsurface ocean could theoretically contain the chemical ingredients needed for life, and its lack of internal heating means that, unlike Europa or Enceladus, Callisto is not a target for active hydrothermal vent environments but still remains a key part of the conversation about the possibility of life on icy moons. In terms of atmosphere, Callisto is almost entirely lacking one, which means there's no significant atmosphere to support life as we know it. However, it does have a very thin exosphere composed mostly of oxygen, but not enough to provide any meaningful protection or support. This makes Callisto a relatively harsh environment, with extremely cold temperatures and no breathable air. Despite this, studying Callisto's lack of atmosphere offers valuable lessons about the conditions that affect moons in the outer solar system. For students studying atmospheric science and exoplanetary atmospheres, understanding how bodies like Callisto interact with their parent planet's radiation field is essential. Callisto's lack of atmosphere, combined with its distance from Jupiter, makes it a good example of a body that exists in the outer solar system without the influences of atmospheric pressures or weather patterns. In the context of space exploration, Callisto has been the subject of interest for future missions. While moons like Europa and Ganymede are often prioritized because of their potential for subsurface oceans and geological activity, Callisto's low level of radiation exposure makes it an ideal candidate for human exploration. Unlike Europa, which experiences intense radiation from Jupiter, Callisto lies outside Jupiter's main radiation belt, making it a potential safe haven for future astronauts or robotic missions. NASA's Juno mission has provided valuable data about Jupiter and its moons, and Callisto may also be targeted by future missions that aim to study outer solar system bodies with a focus on their habitability or exploration potential. In conclusion, Callisto is one of the most fascinating moons in our solar system, providing essential insights into the early solar system, moon evolution, and the potential for life beyond Earth. Whether you're studying planetary geology, planetary composition, astrobiology, or space exploration, Callisto is a perfect subject for anyone interested in the mysteries of the cosmos. It is a perfect example of a cold, ancient world, where craters and icy surfaces remain frozen in time, offering clues to the past and helping us understand how moons like Callisto evolve or remain frozen in place over billions of years. As future missions like Europa Clipper and other exploratory spacecraft continue to investigate these distant moons, we will learn even more about the secrets Callisto holds and the role it plays in the broader context of our solar system's history.